Okay, today's going to actually be an awesome lecture because I love all the topics that we're going to talk about today. They're all connected with LTFs and noise stability. So we'll see some fun stuff. So last time we ended by proving that the majority function has this formula in the limit for its noise stability at the parameter row. It's this formula with the arc coast or the arc sign, whatever, which we did by using the central limit theorem to reduce it to a problem in Gaussian random vectors, and then we used some geometric reasoning to get this quantity. And I ended by mentioning that actually it doesn't just work for majority. The same thing also works for any LTF of this form where all of the coefficients are small. This is the exact scenario in which you can typically show that this inside random variable, if you think about the xi's as random plus or minus 1, will kind of act like a Gaussian. Well, I'm glad you asked that, Jamie. I can't remember if I stated the exact bounds that you can get before, but I will now. This difference you can show is at most, it's order epsilon. This is like some absolute constant. That's the case for any fixed row. The way I know how to do it, actually you get a dependence on rho too. Like this bound gets worse if rho is really close to plus or minus 1. Although I think that's an artifact of the proof, because this is exact if rho is plus or minus 1. So anyway, for each fixed row, it's like order of epsilon. So that's kind of cool. And let me also say that this means, you know, we also have this concept noise sensitivity, which is sort of the same as noise stability up to some halves and subtractions and things. But let me write out what this means for noise sensitivity. It means that this is approximately arc cos rho over pi. 1 minus 2 delta. Because it's like half minus half times this with rho equal to this. Remember, noise sensitivity is like, what's the probability that the outcome will change if you pick a random input and then flip each bit with probability delta. Okay, and this is something that I mentioned actually a long time ago, and I observed that if you like do the Taylor series for cos, you see that for small delta, this is order of root delta. You can even put a right constant here, but I won't bother. Okay. Now, one thing that will eventually, this shows that the majority function and all sort of LTFs where no one variable is very influential have the same noise stability, roughly. It's this thing. And one interesting thing about LTFs is somehow they're the most noise stable Boolean functions. I mean, they're really stable to noise compared to most things. In particular, you know, this thing does not depend on n. It only depends on delta. And that's a bit unusual among Boolean functions. There's, in fact, a theorem that we're going to prove eventually in this class called majority is stablest, which is originally proved due to some applications in hardness of combinatorial approximation, but it's just a nice theorem also about Boolean functions. And it says the following. We'll eventually prove this theorem. Fix some rho that's between 0 and 1. And let's let f be a Boolean function that's unbiased. Okay, so it's expectation 0. Okay, you can think about this all in terms of like f being an election scheme. So it's a function, an election scheme that's not inherently biased towards either of the candidates. And let's further assume that each coordinate has small influence, which is also a natural assumption in the context of voting. To assume that, you know, there's no one voter that unduly influences the election. Then actually, its noise stability, something that you'd want to be large for an election scheme, equivalently you'd want the noise sensitivity to be small, cannot really be any bigger than what it is for majority. So it's at most this thing that it is for majority, plus some quantity which goes to 0 as tau. This tau goes to 0. So as long as all the influences are small, the extent to which your noise stability can beat this quantity is also small. OK, so it sort of says that, in some sense, majority is the most noise stable election scheme. Although actually it's a bit of a misnomer because, as you see from this fact, all low influence linear threshold functions also achieve this value. In fact, just to make this misnomer sound even a little bit more funny, this is about like all Boolean functions. But suppose you only consider linear threshold functions. We know that if all of these coordinates are small, the noise stability will be like this, or the noise sensitivity will be like root delta. What is sort of the opposite case, if you will? The opposite case is like if one of the coefficients is really big and all of them are really small. Or the most extreme case would be the dictator function. F of x equals, as we saw, sine of some xi, in other words, just xi. And that's even more noise stable. Right? For this character, a dictator, the noise sensitivity at delta of a dictator is just equal to delta. Because the dictator election only flips if the dictator's vote flips. And delta is even smaller than this root delta. So actually, the more concentrated the coefficients are on one coordinate, the more noise stable it seems to become. Which actually makes you conjecture that among LTFs, majority should actually be the least noise stable function. I mean, it seems that way, since we know it gets worse as you go to majorities. And this is actually a conjecture made by Benjamini, Kalai, and Schramm in 1999. You may call it the majority is least stable conjecture, just to be confusing.
Is that actually what they called it?
No, they just stated the thing. They didn't give it a funky name. Here, there's always like an implicitly among something. This is among LTFs. And this is sort of among functions with all small influences. And here, you don't even necessarily need any errors. I mean, you can just straight up conjecture that let f be an LTF on n, let's say n is odd, inputs, just for simplicity. Then, for all rho, you may conjecture that the noise stability at rho of f is at least that of majority. That seems very, very natural and expected based on, I don't know, what else could like the least noise stable LTF be but majority? But we do not know how to prove this. No, I don't think so. In fact, actually, we'll see this more later. If you look at the noise stability of a function f, it's like the weight at level 0 of f plus rho times the weight at level 1 of f plus rho squared times the weight at level 2 of f. Let's say you only worry about LTFs that are unbiased. So the mean is 0. In that case, this term goes away. So now if this is really going to be true for all rho, it has to be true when rho is really, really close to 0. And when rho is really close to 0, all this stuff with a higher power than 1 on rho is kind of negligible. So it's like this is saying that the weight at level 1 of this guy is at least the weight at level 1 of this guy. And by calculation, we know the weight at level 1 of majority is asymptotic to 2 over pi. So this essentially includes that conjecture I mentioned last time, saying that every LTF has weight at least 2 over pi at level 1 and below. OK. Well, this, again, conjecture is like more for fun than anything else. Although you see, if it's true, if we just inverted this, it would like say that the noise sensitivity at delta of f is at most the noise sensitivity at delta of majority of n, which we know by calculation is theta of root delta. So if this conjecture were true, we would know this fact, that all LTFs have noise sensitivity at most constant root delta. And that we do know. That's a theorem. So we know it up to a constant at least. And that's something actually I want to prove now. It's called Perez's theorem. This is from 94. No, wait, not 94. I guess he published it in 2004, but he knew it in like 99. And it just says this. For any LTFF, the noise sensitivity at delta of f is at most O of root delta. You can get a pretty good constant, too. This is also mentioned on homework. If you remember that homework 2 or something, homework 3, this has some nice consequences for learning theory. It gives you efficient-ish learning algorithms for a bunch of classes connected with LTFs. OK, and one thing that's fun about this theorem is that it actually, you don't need any like central limit theorem or anything. It's quite elementary. So it's kind of fun to prove. I'm going to give, there's a few variants on the proof known. I'm going to give one that was kind of given by Gopalan a little bit after Perez's paper. OK, and we're going to need one basic fact for this proof, which is that if f is an LTF, then its total influence is at most root n. Anybody know why this is true? OK. Well, suppose if f were, well, let's say is, monotone, suppose I give you that it's also a monotone LTF, then can you say why it's true? All right, perhaps you may or may not remember, but I think in like lecture 2 or something, we proved that all monotone functions have total influence at most root n. It's easy. Actually, we proved that all monotone functions have total influence at most that of majority, which is, I don't know, root 2 over pi times root n. But actually, there's a very trivial argument that it's at most root n. That was using the fact that the total influence of a monotone function is equal to the sum of the degree 1 Fourier coefficients. The influence of the ith coordinate equals the degree 1 Fourier coefficient for monotone functions. And this, as we saw, is maximized by majority. So that's OK. So if it's monotone, then this is easy. Otherwise, somebody have a suggestion?
Influence won't really change if we split the sign of the variables.
Exactly, yeah. Basically, a monotone function, an LTF is essentially monotone, except that you might have to reverse the notion of true and false for some coordinates. Right? If all of the AIs are, well, actually, just look at it. If AI is positive, then the function is monotone in the ith direction, because this quantity can only go up if you change it -1 to 1. And conversely, if it's negative, it's like anti-monotone in that direction. OK, so well, anyway, any LTF is either monotone or anti-monotone. In each direction. So you could like flip the sense of what true and false are for some input coordinates and make it monotone. But that does not change the total influence of a function, just reversing the sense of true and false. It's just like you take your hypercube and you like draw its mirror image or something. So that doesn't change the fraction of edges, which are bichromatic. OK, so well, I don't want to write anything else, but that's the end of this facts proof. Any questions? OK, so good. So LTFs are essentially monotone. These functions that are monotone one way or the other in each coordinate are sometimes called unate. I don't know if you've heard that term. OK, so now let's get to the real proof. Okay, so here's actually a general theorem about noise sensitivity and how it relates to total influence. And we'll prove this general theorem, and then you can immediately apply it to LTFs to get the desired bound. So it's a bit long to state, but let's C be a class of Boolean functions which is closed under negating variables and also identifying variables. Okay, so that means if you have this function and you like reverse true or false for one coordinate, the resulting function is still in the class. And also if you sort of set two variables to be equal, like x3 is always the same as x7, it's still in the class. And say you also know a good a good total influence bound for any function in this class. So say for all n-bit functions, we're eventually going to apply this to the class of LTFs, in case you're wondering. F in the class, you have the total influence of f is at most some function a of n. Okay, and we're going to apply this with the function square root n. Then you can get a noise sensitivity bound for the class. The noise sensitivity at 1 over m of f is at most 1 over m times a of m for all integer m at least 2 and f in the class. Okay, so why does that prove Perez's theorem? Well, as I said, we're going to apply it to the class of all LTFs on any number of coordinates. So, yeah, why are they closed under negating variables? That's easy, right? If a general LTF looks like this, sine a0 plus a1 x1 plus dot 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 plus an xn. If you replace, let's say, x1 with negative x1, then that's the same as like replacing a1 with negative a1. Okay, so that's still in the class. And identifying variables, it's also easy to see because, like, let's say you identify x1 and x2. You just call them the same variable. Then, you know, that's just like getting plus a1 plus a2 times y, if you set them both to y. Okay, so that'll give you an LTF on one fewer variable. Okay, so this theorem is applicable to LTFs, and then we would take this to be square root n by that little fact. And so as a corollary, we get that the noise sensitivity at 1 over m of f is at most, well, 1 over m times square root m, 1 over root m for all LTFs f and for all integers m. So that proves what we want for all delta that are of the form like 1 over an integer. But then you can get what you want for all delta. Because noise sensitivity at delta is like at most, noise sensitivity is increasing function of delta. You can see that from the Fourier formula. So we can replace this by like 1 over the, I don't know, floor or ceiling of 1 over delta. You can round it up to the next 1 over integer. Okay, and this will be at most root delta. Okay, so you lose like some small constant. Any questions about this deduction? Okay, so let's prove the theorem then. And this is a fun proof. I like it. Okay, so basically we know something about the total influence of functions in the class. We want to understand something about the noise sensitivity of functions in the class. All right, so let's fix m. And let's remember what we're reasoning about here. Noise sensitivity at 1 over m of a function f. By definition, this is the probability over x and y. that f of x differs from f of y, where we form x is uniform, okay, and y is flip each bit of x, negate each bit with probability 1 over m independently for each coordinate. Okay, and what we're going to kind of do is describe it like a funny way of doing this exact experiment. Okay, and the brief and incomplete version of this is, what we're going to do is choose x uniformly at random. So it has n coordinates. Somehow this is me writing down a whole list of n uniformly random bits. And then we're going to randomly partition the coordinates into m blocks, into m parts. So maybe this is step 1 is choose x. And step 2 is randomly choose a random partition pi of the n coordinates into m parts. Okay, and what do I mean by a random partition? You just go through, you're going to have m parts. You just go through each coordinate and pick a number between 1 and m for it. And that's the part that it goes into. Okay, so I don't know, maybe like this goes into part 3, and the next coordinate goes into part 2, and the next coordinate goes into part m, and so forth. But eventually you'll get something like some block of the coordinates will be part 1, and some block will be part 3. That would include this one, and so forth. You guys get it? Okay. Great. Now, step 3, and go back to black. Step 3, just pick j uniformly at random from 1 through m, and form y by negating the ith part, jth part. That's a good point. It does not have to be random. You could actually do this just by negating part number 1. And that would, okay, what I want to say is this actually gives us the correct distribution on x and y. Okay, because for each coordinate, what's the probability that you flip it? It's the probability that it appears in the jth part, which is 1 over m. Now, as was pointed out by, I forget, Brian? I mean, I wasn't looking when somebody said it. Brian. Actually, j does not even need to be random here. You could just flip the first part, and that would still give the correct distribution. But we're going to actually add a couple of more Baroque twists to this for our purposes. And like this is one such twist. We're actually going to flip a random part. OK, so does everybody agree, though, that with this weird way of doing the experiment, you still get x and y as you want? Great. OK, so now here we'll do an extra twist, which is we also don't need to do it, but we're going to do it for analysis purposes. So I'll call it step 2.5. I'll sneak it in here. Pick a random string z of m bits uniformly. And now I want to define x prime by multiplying the ith part of x by zi for all I. And I want to slightly modify 3 so that I form y from x prime rather than x. Now, all I want to claim is that having done this experiment, I claim that x prime and y have the right distribution, this distribution. Okay? And actually, the only thing I need to check is that I just did what I did before with x, only with x prime. So I just need to check that x prime is a uniformly random string. And it is. Like, I just took a random string and then like multiplied it by some bits in like a non-independent correlated way, but it doesn't matter because the thing was initially uniformly random. Yeah, so for all, so like I'll multiply every coordinate in here by z1, which is either plus or minus 1. I'll multiply everything in here by z3, including this guy, which is plus or minus 1, and so forth. OK, so I've, for some odd reason, defined this strange way of generating these like 1 over m noisy strings. A string and like another string where each bit is flipped with probability 1 over m. So, OK, so we know that we may still say the noise sensitivity at 1 over m of f is equal to the probability f of x prime differs from f of y. This probability is over this now somewhat crazy experiment of choosing x, pi, z, j. OK, and x, pi, z, and j define x prime and y. OK, so that looks weird. Hopefully you'll see where this is going soon. So now I'm just going to break it up by like first doing x and pi, then doing z and j. So you can break that up by doing an expectation of the probability. OK, so now this is where we need to start thinking a little bit hard. So like imagine x and pi are totally fixed. OK, and now we're just going to think about what's going on with the choice of z and j. So what that means is I totally fixed x. So it's like a random string. But then I fixed it. And then I also fixed the partition. And now the remaining part of the experiment is to choose z, which is to like basically has the effect of either negating or not negating each of the blocks simultaneously, and also to pick a block randomly. So what I claim is this is where you need to put your thinking cap on. This is g sub z, wait a minute, x pi of z. And this is g sub x pi of z with the jth coordinate flipped, where g, x pi, is a function on m bits defined by, let me say, it's like the map that maps z into f of like x, with its ith part sort of under pi multiplied by xi. Zi, sorry. Okay. I'll write that in like mathematical terminology over here, but think about it for a second. What I'm saying is I want to, for each fixed x and pi, define a function g on m bits. It'll be a Boolean function that just on input z tells you like what's f's value if I do this sort of thing. Multiply the ith block of x by zi for each block. Okay. So to write it mathematically here, another way to define g sub x pi on a string z is like f of like x1 times z pi of 1 through x n z pi of n. Right, where you think of pi as a mapping from n to m. Okay, remember here x and pi are fixed. Z's are like the variables. Yeah, so that's exactly x prime. And then y I get by negating everything in the block, which is sort of the same, the jth block, which is the same. It's like doing g on z with just the jth coordinate flip for G. Do you like it? Do you agree with it? Okay, this is a little weird. This is a function of the z's. The x's are constant there. Okay, so I also claim that this is gotten from f by negating and identifying some variables. Does it? Actually, having written it, like I was like, oh, how do I explain this?
You identified all the variables for which you mapped. Yeah, the Z pi of phi.
Yeah, it's like you've taken all the variables in like the first part and identified them and called them Z pi. Yeah.
They aren't all the same, though, right? I mean, you're either negating them or not, but
Exactly.
Yeah, for each kind of part,
You're doing that
doesn't
together,
identify mean that you're
like,
like,
to all of them the same way.
yeah.
yeah, but they don't all turn into the same.
Suppose you first negate some of them based on x, and then you identify them based on pi.
Right.
I don't understand what identify means.
Like you take like 5 variables and you say these are, I'm going to substitute like y or z for all of these guys. So it's like, normally you have like,
Yeah, okay, I see.
yeah. So it's like you've substituted a variable called z pi I for each original variable in the ith block. And you also, as Misha said, the first thing you do is like potentially plus or minus each guy in the block based on what x is. You know, even saying it now, like I'm thinking to myself, yeah, I'd really have to like really like sit down for 2 seconds and convince myself that it's true. But it is true if you go home and reflect. But it's true.
Kind of like negate some of them.
Yeah.
Then you do the identification. Then you negate back the ones that you negated before.
I don't think you should have to negate twice.
Because, you know, like,
Really what we're doing here is we're taking f, which is defined on n things, and we're taking like m symbols, z1 and z through zm, and we're substituting for each coordinate of f one of the z symbols or possibly negative of one of the z symbols. Yeah. So it's like, yeah, you're like plugging in like fewer than n new variable names for the n original variable names, and also possibly throwing in some minuses.
So take f, you negate all the x tells you which variables to negate.
Yeah.
Okay.
Yeah. Yeah, so the x tells you which variables to negate, and like pi tells you which variables to identify. Great. All right, yeah, I feel pretty good about it now. Good. All right, well, there's only like 2 lines left in the proof. So once we finally believe that, we're here. Great, which means that this thing is in the class by assumption. So therefore, its total influence is at most, oh, wait, I'll get to that in a second. Right, so anyway, star, okay, so what's going on in star? We have, its expected value over x and pi of some experiment, probability over z and j, that g sub x pi of z does not equal g sub x pi of z plus j. Okay? So it's almost like it's the average influence of this function g on the inside, right? You're taking a random string. Like if you first you fix j, you're doing the experiment for the jth influence. Pick a random string, flip the jth bit, see what the probability that it flips. And so, yeah, I mean, I can even write this as expectation over j, probability over z. So this is the jth influence of this g function, so you're taking the average influence. Okay, and this G has m coordinates, so this is really just expectation over x and pi of 1 over m times the sum of the influences of G, so total influence of G. Okay, but as we eventually argued, G is in the class, it's on m variables, so its total influence for every choice of x and pi is at most a of m. Okay, any more questions about that? It's kind of slick. Yeah, that's all I can say. It's kind of slick. Yeah? These two? This is because this is the, once J is fixed, this is the influence of the jth coordinate on G. And I'm really just changing this expectation over J into like 1 over m times the sum over J. Because J is just uniform between 1 and m. So I have 1 over m times the sum of the influences of G. Okay. Okay. I want to make a brief, so that's the end of one thing we'll do today. Let me go back very quickly to this thing that I started with, which is the formula for the noise stability of majority in the limit. I just want to make one more random side comment about it, and then we'll move on to a slightly different topic.
Excuse me?
Yeah.
A minor point. So for this, you would have to, we have to define majority, for instance, over even times.
Oh, that's an outstanding minor point. I should look into that. No, I guess, yeah, what you're saying here is that once you identify some variables, it might no longer get an LTF because you could get into a situation where the linear form of this identified function has the potential to evaluate to 0. There's a couple of ways to get around that.
How does that happen?
Well, I mean, let's say f of x was originally sine of x1 plus x2. Oh, maybe it can happen. I don't know. x3. Let's see. No, you're right. It can't happen. Because I thought, oh, you'll identify these two things and call it, let's say they both are y. Yeah, but now y is a coefficient of 2. Yeah, any value achievable by the linear form originally, any value achievable by the new linear form was achievable originally by the original linear form. Does that answer your question? You tricked me, though. That was good.
Because what you had written was you had written for all n bits, which influence should be less than. So I thought that for all values of n, you should be able to define the influence.
Yeah.
If the sum of coefficients is odd, it can't be 0.
Well, once you do the identification, it's not majority anymore, it's weighted.
Yeah, okay.
So we know how to calculate the
It's also, yeah, it's also okay. I mean, it's fine to let the linear form take on the value 0, just to find sine of 0 to be either 1 or minus 1, your choice. And actually, everything is still true. But okay. All right. Let me briefly say this thing about noise stability of majority. Okay, so one thing we stated and proved last time is the noise stability at rho of majority on n variables tends into the limit to this fixed function involving rho, which you can write in terms of arc sine or arc cos. I'll write it in terms of arc sine here. Okay, so if you've taken real analysis, you probably know how to compute the Taylor series of this thing. And it turns out it's this. excuse me. The Taylor series of arcsine is apparently rho plus 1 over 6 rho cubed, excuse me, plus 3 over 40 rho to the 5th plus some other stuff. And yeah, it's only got non-zero coefficients on the odd stuff. It's an odd function, and on the kth coefficient, on rho to the k, you get 2 over k minus 1, choose k minus 1 over 2, over 2 to the k. Okay. Does anybody know how to actually do that? Yes, that's right, that's right. That's right. You take the derivative, and then you get like 1 over root 1 minus rho squared, and that you can like get the Taylor series for by like the general binomial theorem, and then you integrate. Very good. You've taken, you know your math. Great. Okay, so on the other hand, we know the Fourier formula for this. It's this. It's the weight at level 0 of majority. Okay, let me just write WK for the weight at level k of majority. So it's the weight at level 0 plus rho times the weight at level 1 plus rho times the weight at level 2 plus rho times the weight at level 3 plus dot, dot, dot. That's the formula. And yeah, thank you. Rho squared, rho cubed, etc. And majority is an odd function, right? If you negate all the bits, that negates the outcome. So you saw in like homework 1 or something, that means it only has non-zero Fourier coefficients on odd levels. So this is actually 0. This is actually 0, and so forth. So then if you stare at this, you say, huh, I kind of think that I should just be able to match stuff up term by term and guess that for odd k, the weight at level k of majority on variables tends, as n goes to infinity, to 2 over pi times this. Seems like it should be true, right? Yeah, so actually that's true. And in fact, this is not even a fake proof. You could actually turn this into a real proof.
The kind of thing that analysis allows you to do that you really shouldn't be allowed to do.
No, you should be allowed to do it. It's awesome. You can actually do this by, well, does anybody want to, who's done this stuff, suggest how to actually turn this into a proof? Well, I'll tell you. We know that this holds for all rho. So you can take rho to be really, really small to start. And then you know that this is like 2 over pi rho plus something that's like O of rho cubed. And this is also like rho times weight at level 1 times O of rho cubed. So because it holds for every rho, you can actually just, it has to hold with equality for the main term. So you can deduce that you have this formula at least for weight at level 1. And then once you know that it's exactly correct for the weight at level 1, you can again take like rows really small, and like the first terms match up, and then you have the second terms, and then O of rho to the 5th. And you can argue that it should work for the third term, etc. Anyway, so this is a fact. In fact, you can just compute the exact Fourier coefficients of majority in terms of n and k. But it's not very enlightening. So this is actually what you should remember. And this is asymptotic to, in k, what is this asymptotic to? Up to a constant.
2 over k root k.
Say again?
2 over k root k.
Yeah, I'll drop the constants, but it's like, yeah, 1 over k to the 3/2. Because this thing is like 1 over root k. And you have another factor of k. OK, so this is a good thing to remember. It sort of tells you exactly how the Fourier weight of majority, this most important function, is distributed. In fact, it even also tells you that if you look at the weight above level k, this is sort of the Fourier tail, the amount of Fourier mass it has above level k, it tends in the limit as n goes to infinity. Well, to like the sum of this as k goes from like k to infinity. So that's like 1 over root k. OK, so majority has something like 1 over root k weight above degree k. And that's sort of consistent with the fact that its noise sensitivity at delta is like root delta. And this is actually sort of this is like saying if you plot the Fourier weight in terms of k, it goes down like this. And like, no Boolean function can actually have its Fourier weight decay faster than this unless it's close to being a junta. That's a theorem of Bourgain, which we might get to by the end of the class. OK, that's a side fact that I wanted to tell you for culture's sake while we had this formula up. OK, so for the rest of the class and also a good chunk of the next class, I want to actually get away from LTFs and just go back to studying general Boolean functions. And I want to study a very specific quantity, the weight of the function at degree 1. Okay, this turns out to be a very interesting quantity. We're going to prove 2 theorems about it. One is called the level 1 theorem, and one is called the 2 over pi theorem. I'm going to state them today, and then we'll prove them next time. But first, you may ask why. Why would I care about this function? At first, it does not seem to have any obvious meaning.
Did you prove something about these at homework?
Did we? Yeah. We proved that if this is 1, then the function has to be either a dictator or an anti-dictator. Yeah, actually, you're proving something about that in this homework, too. There's a theorem about this called FKN theorem that says if this is close to 1, then the function has to be close to either a dictator or an anti-dictator. It's much harder. OK, so why care about this function? Well, let me tell you a story, or this quantity. Let me tell you an interesting story about the Boolean hypercube. OK, so say f is any old Boolean function, and I'm going to think about its range as being 0 and 1. So geometrically, you may think of f as the indicator of a subset of the cube. I can say f is the indicator of some set A, where A is a subset of the cube. So I want you to think geometrically now about subsets of the discrete cube. And I want to fix in my head the volume of this set, if you will. So I want to fix alpha, or write alpha to be the expectation of this function. It's 0, 1 valued, so that's the fraction of points which are 1. This is like the cardinality of A over 2 to the n, which you may think of geometrically as like the volume of the set. Normalized volume between 0 and 1. OK. Now, one thing that is an interesting quantity, undoubtedly, is the noise stability. We'll see in a second how to think about that geometrically. So the noise stability of, sometimes I write f, sometimes I write 1 sub a. Well, anyway, it's the same thing. The noise stability, we have this formula. It's the weight at level 0 plus rho times the weight at level 1 plus rho squared times the weight at level 2 plus et cetera. We know exactly the weight at level 0 because the expectation we fixed to be this alpha. So that's the degree 0 Fourier coefficient. So this is just alpha squared. OK, so think of that as like a constant in your head. OK, and so now you may write this as, now you may think of rho as being very small, just like we did over here, in which case this is the weight at level 1 of f times rho plus all of the weights add up to 1, and they're getting multiplied by a coefficient which is no bigger than rho squared. So this is like O of rho squared, if you think of rho as going to 0. So you see, basically, the weight at level 1 controls the noise stability when rho is really small. Okay? If the weight at level 1 is big, if and only if the noise stability for small rho is big. Okay? They go together. In fact, I mean, you can see this easily. the weight at level 1 has some kind of meaning. It's the derivative of noise stability of f evaluated at 0. Okay, this holds for any f, even an f into the reals. Just because you take this formula with weight 1 here, differentiate with respect to rho, and then plug in rho equals 0, you'll just get this coefficient. Okay, so basically measures like noise stability for very small values of rho. Okay, so asking about questions like which function maximizes noise stability, which function of a given volume maximizes noise stability for small rho is kind of the same as asking about which function maximizes the Fourier weight at degree 1. And forgetting about rho being small for a second, this question about maximizing the noise stability or looking at the noise stability of sets of fixed volume is kind of interesting. It's like an isoparametric question. So let's see why that's the case. This noise stability of rho at, let's say, the indicator of A, well, by definition, it's equal to the expected value over x and y rho correlated strings of 1a of x times 1a of y. Okay, but this function is just the indicator of A, so I may write this as the probability, I shouldn't have erased, oh well, the probability that x is in A and y is in A. Okay, it's the probability if you pick two correlated strings that they both land into A. And I may also write that like this. It's the probability over x. Well, let me just say it's the probability over x and y that x is in A times the probability that y is in A conditioned on x being in A. Okay, that's just by definition of conditional probability. And this, x is uniformly random, so this is just alpha. So this is alpha times probability, x and y rho correlated, that y is in A given that x is in A. Okay? Or in other words, just dividing this by alpha, this probability is equal to the noise stability over alpha. Okay, so thinking of alpha as a constant, the noise stability of this function, after dividing by this constant, tells you this quantity. What's the probability that if you take a random pair of correlated strings, condition on the first one falling into A, that the second one will also fall into A? And this kind of measures in some ways, the size of the boundary of this set A, but not in the usual hypercube, but in some kind of like noisy version of the some version of the hypercube where the edges are like long distance edges rather than just Hamming distance 1 edges.
How is it?
Pardon me?
Like, how is it hypercube?
Roughly, yeah. Because in this experiment, it's roughly like x and y are going to be at distance. Well, the inner product of x and y will be something like rho times n. So they'll be very close to some fixed Hamming distance. So it's kind of like if you did, well, anyway, let me write what I'm going to write. So let me make a sort of a definition. I'll call it the rho stable hypercube. You can think of this as like a weighted graph whose vertices are the vertices of the hypercube, but has different edges than the usual edges. But I actually prefer to think of it as a Markov chain. Okay, so it's a Markov chain where the state space is the vertices of the cube. I'm drawing the usual edges in, even though they don't really play a role here, but just so you can see what the picture is. Where the state space is minus 1, 1 to the n. And like the transition is, if you're sitting at vertex x, then you just go to Oops. If you remember this notation, like this row noisy version of x, this is where the operation where you, at x, for each coordinate, you hold it steady with probability rho, and you re-randomize it with probability 1 minus rho. So like in this Markov chain, you're sitting at a thing, and then in one jump, you like go to like a row noisy version, and another jump, you go to another row noisy version, and so forth. You can think of it's like a symmetric, reversible Markov chain. So you can think about it as like a weighted graph too. So you can think about subsets of the vertices here, or the states, like A. And what this is measuring is, like, if you pick a random, Markov chain is the uniform stationary distribution too. So if you pick a random vertex in A and you do like one jump, this is saying what's the probability you'll stay inside A. Okay, so it's some measure of the expansion of the set A. So this is really like the expansion of A in this Markov chain. Does that make sense? Any questions about that? It's the probability you'll like escape from the set A in one step. It's the probability you'll stay in A in one step. Thank you. Yeah. Right. Yeah, it's like it's like 1 minus the expansion. Thank you. Okay, good. So the hypercube has this interesting property called small set expansion, which roughly says that every small set of the hypercube has huge expansion, which means that if you have any small set of the hypercube, if you do this, pick a random point in it and do one jump, you're extremely likely to exit the set. Okay? It'll be like 1 minus something small that you'll exit. Which is not true if you only look at small sets. Like if you take a set of volume a half, like a dictator, all the things with one coordinate equal to 1, if I pick a random point in this half, do one step, and ask what's the probability I exit, if I ask what's the probability I stay, it's like half plus half rho. It's just whether I randomize that coordinate or not. So it's not close to 1 necessarily. Kind of. This says if you're doing a random walk, you will not get stuck in any small step because you're very likely to exit any small step. Although, as I was trying to indicate poorly, this graph isn't really an expander because there are sets of constant volume, half volume, which don't expand very well. So kind of, I mean, that great. So kind of, if you're on this half of the cube and you do some steps, you have some chance of like staying on that half of the cube for a while. But if you only look at small sets, you're unlikely to stay inside them. Okay, so there's a theorem to this effect, which I might call the small set expansion theorem for the hypercube. So it's basically proved by KKL. I mean, if you look at what's going on in their paper, it's basically this. And what it says is this quantity, let's say star, is at most alpha to the 1 minus rho over 1 plus rho. You can state the theorem with very few symbols. So let me plot this for you. Okay, so this is the rho axis. Remember, this is in the Markov chain, like what's the probability that you hold the coordinate steady as rho? So when rho is 0, you get alpha. When rho is 1, you get 1. So it looks like this. Okay, remember, this is the probability that you stay inside A when you do one random step in A. And it makes sense. If rho is 1, you don't have actually, the walk doesn't change. It just stays at the same point always, so that's 1. If rho is 0, that's like you just jump to a uniformly random point at every step, so the probability you'll go into A again is alpha. But the point is when alpha is small, this is really close to, I mean, if rho is some arbitrary number in the middle, like a half, then this is like alpha to the 1/3. Okay, so it's still like asymptotically small if alpha is small. Probability of you stay in a set is still close to 0. It's like alpha to 1/3. Okay, so we'll eventually prove this theorem, not that long from now. But you need this like hypercontractivity, which we haven't gotten to yet. But you need the hypercontractivity to prove it for every value of rho. But so I was arguing here, like the weight at level 1 is somehow capturing what's going on with rho really close to 0. And in that regime, actually, you can prove things with elementary means. So there's a kind of a special case of this theorem for a really small rho, although it's really like a theorem about the weight at level 1. And this is one of the theorems we'll prove next time, called level 1 inequality. All right, and it says let f be any Boolean function into 0, 1. Let alpha be the mean of this function. And assume it's at most half. Okay, this is just if it's not at most half, you can look at 1 minus f. So think of f as the indicator of a small set. Then the weight at level 1 of f is at most O of alpha squared log 1 over alpha. Okay, and I'll say in 2 seconds why you should think of this as like remarkably small. So what that's saying is if alpha is small, if you're the indicator of a small subset of the cube, this thing is very small. And as we said, this weight at level 1 is kind of like a proxy for your noise stability for small rho. So it's expressing this idea that small subsets of the cube are very noise sensitive. They have very low noise stability, like unusually low. Okay, so this is one statement of that phenomenon. You can actually, we know that this weight at level 1 is something like the derivative of noise stability evaluated at rho equals 0. And you actually derive this theorem by like differentiating this equality and substituting in rho equals 0. But that involves first proving this inequality, which is a bit of work. But this you can prove in an elementary fashion, which we'll do next time. And why do I say this is small? Well, just to make sure we're getting it. What is the total weight of this f, the 2 norm? The sum of all the weights. Can somebody tell me what it is? Nope. Yes, alpha. Because if you think back to lecture 1, this is the most basic of all theorem, Parseval, tells that this, this is Parseval right here. It says that this is the expected value over x of f of x squared. Parseval says that the sum of the squares of the Fourier coefficients is equal to the expected square of the function. And f is 0, 1 valued here. So if you square it, this is the same as f. So this is the same as the expected value of f not squared, which is alpha. Okay, so the total Fourier weight to go around is alpha. Can somebody tell me the Fourier weight at degree 0? Yeah, alpha squared, because this is, just by definition, this is f hat empty set squared, which is the expected value of f squared. I'm writing too low, evidently, which is alpha squared. Okay, so the total weight, just as soon as you fix, it's a 0, 1 function, as soon as you fix its mean to be alpha, think of alpha as small, then you know the total weight, Fourier weight to go around is alpha. At level 0, it's like negligible, it's alpha squared. So potentially this weight at level 1 could be as much as alpha, but The theorem says it's like much, much smaller. It's basically like alpha squared.
Doesn't that give us like a strong, doesn't that say it should be about alpha? For a small row, that's like about alpha to the 1.
Yeah, so let's see. I mean, I don't know if it wasn't. Let's try to do it. So remember, this thing star is the stability at rho divided by alpha. So this would be equivalent to saying the stability at rho of 1a is at most alpha times this. So I have to add 1 to this exponent. So I'd get 2 over 1 plus rho. So can anybody differentiate that? I cannot. Can anybody do like d by d rho alpha 2 of 1 plus rho valued at rho equals 0? Anybody have a computer? OK, well, anyway, let me think about it. Oh, you get 2 alpha squared log 1 over alpha. Maybe ln? Either log or ln. I'm not sure. Anyway, so you can actually get like an explicit constant here. Actually, the sharp constant is 2. OK, so this is one theorem that we'll prove next time, and it's actually useful in a variety of contexts. It captures this fact that to some extent, it captures the fact that small sets in the hypercube have huge expansion. It's also used in other places, like in additive combinatorics. This is called Chang's inequality, and it's used for other stuff. But it's actually first proved, I guess, by Talleyrand. Although, really, you can get it by differentiating this result from 88. So, OK. So that's one theorem we'll prove next time. Oh, and let me just give some illustrations of it as well. Let's check it on a couple of simple examples. So here's a nice set. A is a set of all x such that x1 equals x2 equals xk equals 1. OK, so the indicator is like the AND function of k variables. OK, so can somebody tell me the expected value of 1a? Just shout it out. Like, what's the probability that a random point will satisfy this? Yeah, 2 to the minus k. OK, and now let's also compute the weight at level 1. Well, f hat I squared is certainly going to be 0 if I is bigger than k, because the coordinates bigger than k are irrelevant. If I is less than k, I think this is on like one of your homeworks, basically compute the degree 1 Fourier coefficients of AND. I think it's going to be 4 over 2 to the 2. Yeah, just 1 over 2 to the 2k, I think. I think the non-squared coefficient is like just 1 over 2 to the k. Great. So therefore, the weight at degree 1 of this guy, the AND function, is you get this k times. So k times 2 to the minus 2k. OK, and if we're calling this alpha, then this is alpha squared. And this is like up, well, it's up some constant times log of 1 over alpha. OK, so we see that actually this cannot be improved by more than a constant. It's sharp for the AND. Yeah, so whenever you're thinking about like interesting and unusually noise-stable functions in the cube, you should think about cubes, like this one, and balls, Hamming balls. So let's try a Hamming ball. So we need a Hamming ball with some small volume. So let's call this, instead of all x in minus 1, 1 to the n, such that the sum of xi, I goes from 1 to n, is at least some t times square root n. OK, so this is a Hamming ball with radius n over 2 plus half times t root n. think of t as a parameter. And on your homework, I asked you to calculate these two things, the expectation and also the weight at level 1, which you can do very easily using the central limit theorem. So the expectation of this thing, it's like what's the probability if you take a random string that the sum of the bits will exceed t over root n. Actually, let me make it more like this. 1 over root n times xi. Well, basically, this acts like a Gaussian. So it should roughly be the probability that a Gaussian exceeds t. So that's integral from t to infinity of the PDF of a Gaussian, which I'll write as phi. This is sometimes the complementary, called the complementary CDF of a Gaussian. And it's known that it's basically like phi. It's like phi of t over t. These are like calculational facts that you may not know, but that's true. So in your homework, you're also asked to analyze what's the weight at degree 1 of this Hamming ball. And you will find that as n goes to infinity and t stays fixed, it's like phi of t squared. This is the Gaussian PDF. Great. So if this is what we're calling alpha, and this, you see, is basically alpha squared. It's like alpha squared times t squared. Yeah. And what is t in terms of alpha? Like phi of t over t equals alpha. So t is, it's basically something like phi inverse of alpha, which you can check is something like square root log 1 over alpha. Because in the Gaussian PDF, you have like e to the minus t squared. So if you invert that function, it's square root log 1 over. OK, you don't have to follow all these calculations if you don't want, but it's to show that if you again plug this in, you'll again get alpha squared times log 1 over alpha. OK, so actually, Hamming cubes and Hamming balls saturate this inequality up to a constant. They're somehow, actually, Hamming balls are like the most noise stable small set in the cube.
What happens to smaller balls, like radius case?
Oh, like if this really like, if the Hamming radius is, instead of being like n over 2 plus constant times root n, but like n over 4 or something.
Or even some independent case?
I'm not sure. I would guess that it's still, I don't know. One could calculate it, though. OK, so that's one theorem that we'll prove. This is one theorem we'll prove next time. And now let me mention one more fun theorem that we'll prove. So this is all about what happens for the expansion of small sets. Subsets the cube of volume alpha thought of as small. No, but let's go back to the more classic situation of like, or a case where it's not small, where the volume is a half. So in the alpha equals a half case, you're looking at subsets of half the cube, bisections of the cube. Well, first of all, it's more natural to switch to plus or minus 1 notation. So let me think about functions that go into minus 1, 1. And then to say that their volume is a half is to say that the expectation is 0. OK, and you might ask, how can we maximize the weight at level 1 of such functions? Okay, which is kind of like asking for the maximal noise stability or the least expansion for a really small rho. So what upper bound can I put here?
1.
That's right. And that's sharp. Because, well, as we've seen before, dictators and anti-dictators satisfy it. So it looks like very boring and like there's nothing to say. But as we saw in social choice, when we studied it, this is related to noise stability, something that you want to maximize. Dictators and anti-dictators are kind of lame. We don't really like them. We prefer to only look at, let's say, functions where all of the voters have small influence. Okay? Or an even weaker condition that all the voters have small influences is just to say that all the degree 1 Fourier coefficients are small. Let me get the exact bound correct. Okay, and actually for this, I don't even need, if I'm trying to ask about the maximum weights at degree 1, I can even drop this hypothesis really, because you're only hurting yourself if you make the function unbiased. That's like putting a lot of its weight at degree 0. So one can even drop this. Now write a theorem. So this rules out dictators and anti-dictators, and then you get like this jump. You get like this, I don't know, phase transition, if you will. For all I. The theorem is that the weight at level 1 is at most 2 over pi, plus order epsilon. Okay, we need something depending on epsilon here. This is called 2 over pi theorem. And it's kind of fun. It says among functions with all their degree 1 Fourier coefficients small, the most weight you can have at level 1. We saw actually that majority has weight around 2 over pi at level 1. And in fact, there's a cool converse to this statement, which is that if you have a function whose weight at level 1 is close to this, so it's at least 2 over pi minus delta, then it's actually close to an LTF. Maybe root delta, close to an LTF. In fact, it's close to the sign of its degree 1 part. Okay, so we saw last time, actually all LTFs, not just majority, which have small, AIs are essentially small degree 1 Fourier coefficients, have weight around 2 over pi. No, actually, it's with some just degree 1. Because here I just have add exactly 1. So if you're very unbiased, you won't actually satisfy this. So what this says is that actually there's a funny thing. Assuming you reduce to the class of functions that have their degree 1 Fourier coefficients small, then like being an LTF is like robustly characterized by having the property of weight 2 over pi at degree 1.
We had a conjecture last time that for all LTFs, the weight 1 is bigger than, if I remember.
Yeah. Okay, any questions?
What's this f equals 1 thing again?
Oh, this means the degree 1 part. So this is the sign. So namely, f is close to sign f hat 1 x1 plus dot 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 plus f hat n xn. So just take in the multilinear expansion, take the degree 1 part, throw everything else away, take the sign of that, and f is actually close to that. Okay, see you on Monday.